Okay, welcome everybody. Welcome to the first talk of the fall 2021 semester of the New York Group Series seminar. So this semester we're still meeting online because of the pandemic. So we didn't know what was going to happen, but the CUNY Graduate Center, they still not allowing for the moment any in-person talk. We don't know what will happen in the spring, so we'll see. So hopefully something will change. But for this semester, all the talks will be online, and we had to migrate our website, from old Google sites or classic Google sites to new Google sites. So I think that the parent web page address remained the same, but the layout changed, so hopefully people can still find it, and the schedule of the talk is available there. The schedule of the remaining talks is available there. So I think next week Alexey Mesnikov is supposed to speak, if he provides the details of his talk to us. And today we are pleased to welcome our first speaker is Benjamin Steinberg from City College of CUNY, and he's going to tell us something about Cartan pairs of algebras. Ben, please.
So thank you, Ilya, for giving me the chance to speak here, and thank those of you who came out. So I should apologize that that in some sense, when Ilya contacted me about this talk, it was towards the beginning of the semester. So I had to kind of work with whatever I had prepared, and I was giving a talk in a non-commutative geometry operator algebra seminar. So I kind of took those slides and then repurposed them for this seminar. And I particularly added a section called groups, which tries to make more clear how the groups fit in. But the group theory that appears here is mostly group rings, not so much groups themselves. So I apologize that this is probably a slightly off-topic talk, but hopefully it will still be entertaining nonetheless. And you can stop me at any time to explain background stuff, because as I said, this was originally written for analysts, and then I tried to repurpose the slides. Probably it would have been less work to create new slides, but that's how these things go. This is my list of co-authors. You see, it's quite a lot. We actually started as two separate groups working on the same thing, and then we discovered we were working on the same thing, and we decided to join forces rather than to compete. So that's why we have so many people. I guess this paper has just been accepted into IMRN, or did I get the order of those letters correct? So it's just been accepted this last week. So, and let's see, is this actually, oops, it did turn. Okay, that's the outline of my talk. So history, then some groups, then we move from groups to something that sounds a little scary to group theorists called the groupoid. And then I'll talk about Cartan pairs. So the origin of this talk actually starts in analysis. So as I said, this was originally written for an operator algebra style kind of seminar, but I'm not going to assume you know anything about analysis because I don't know very much about analysis. So it'd be unfair for me to assume that you do. So in the 60s, Feldman and Moore introduced what are called Cartan pairs of von Neumann algebras. It's in the same paper where they proved this famous theorem that if you have like a Borel equivalence relation with countable classes, then it comes from a group action. So people who like this kind of measure theoretic group theory often quote this Feldman and Moore paper. It's a series of two papers, and one part proves that. And the reason they wanted that is to kind of show that the kinds of algebras they were studying can also be thought of as coming from groups. So anyway, that's kind of the relation with group theory of that paper. But anyway, a Cartan pair consists of a von Neumann algebra A, and I will not tell you what is a von Neumann algebra, but it's some kind of operator algebra. And von Neumann algebras you should somehow think of as being big operator algebras. So like a commutative von Neumann algebra is basically looking at measurable functions. You have a measure space and measurable functions and pointwise multiplication. So that's in some sense big, as opposed to a Cstar algebra, which you should think of as like continuous functions on a space, which is smaller than measurable functions, than integrable functions. And what Feldman and Moore proved is that all these Cartan pairs, which again I haven't defined for you what they are, and I won't, but they came from groupoids with a twist. So a twist like in the sense of a twisted group ring. So I'll define it, but it's a similar idea to a twisted group ring where you have a group and you have a cocycle, and you can use the cocycle, the two cocycle, to twist the group ring multiplication. So they showed that basically Cartan pairs are twisted groupoid algebras, and the commutative subalgebras come from functions on the unit space. So I'll define later in the talk a groupoid and a unit space. You don't really need to know what these words are for now, but roughly speaking, when you have a groupoid, you get an algebra and a commutative subalgebra. And basically Feldman and Moore showed that these Cartan pairs, which are these nice pairs of, like, the reason they're called Cartan pairs is in Lie theory, as probably everybody knows, a Cartan subalgebra is a maximal commutative subalgebra. And then there's this theorem that they're all conjugate to each other. So these guys were trying to sort of look at maximal abelian subalgebras and developing some kind of Cartan theory there. And one of the things in their theory is that the groupoid and the twist are uniquely determined by the Cartan pair, meaning that basically the groupoid is unique up to isomorphism and the cocycle is unique up to a co-boundary. So the usual things you'd expect. Then, and afterward in the 80s, Kumjian and Renault, first Renault, then Kumjian, and then back to Renault. They didn't work together, they took turns, created a Cstar algebra version of this theory of Cartan pairs. And again, their Cstar theory came from certain twisted groupoid algebras of very special groupoids, and I will define this later in the talk. An étale groupoid is a topological groupoid that thinks it's a discrete group. So a discrete group is an example of an étale groupoid, and étale groupoids are kind of the groupoids that are closest to discrete groups. So I will define all this stuff, but right now I'm just giving history, so you don't have to pay any mind to what it actually is. And again, in their theory, the groupoid and the twist are unique in an appropriate sense. But what I want to talk about is that this theory came up with some surprising applications in symbolic dynamics due to Matsui and Matsumoto. I guess people in group theory mostly know of Matsui because of his work on topological full groups and introducing these kinds of groups that eventually led to the Monod-Yushchenko result on these simple amenable groups. But Matsui was actually interested in groupoids, and he built his full groups out of groupoids. And that's the way he really does it. And he was interested in their connection with symbolic dynamics. And so let me just tell you what's a shift of finite type. So we have a finite directed graph, which operator people always call E. And for simplicity, I'm going to assume the graph is finite. That's not really so important. Directed is important. And I'm going to assume no sinks, again, to avoid some trivialities. And to pretend we're working with the CW complex, I'm going to write E0 for the vertex set and E1 for the edge set. So like the 0 skeleton, 1 skeleton kind of setup. And I'm going to write S for the source of an edge and T for a target, because later I'm going to write some formulas. So then the edge shift on E, the two-sided edge shift, is the space of all bi-infinite paths on E. So you look at all bi-infinite paths, that's essentially, a compact, totally disconnected space. And then you have the shift map, which just basically shifts the, when you look at this two-sided infinite path, you're supposed to kind of mark like the origin of, I mean, it's not, since it's two-sided, what does an origin mean? But it's an infinite, your infinite path is an infinite sequence. So you have something like E0, E1, E2, a sequence of edges, but you also have E-1, and I'll put a decimal point so that you know where E0 starts, and it's two-sided infinite. And the shift map just moves the decimal point 1 to the right or left. Different people have different conventions. So that's a symbol, an edge shift. And up to conjugacy, which is like isomorphism of shifts, these are what are called shifts of finite type. Gromov likes to say shifts of finite type are kind of finitely presented shifts. So I read that he said that somewhere. So these are kind of the shifts that people are most interested in. And if you get bored during this talk, it's a long-standing open question. Given two finite directed graphs, can you decide whether the corresponding edge shifts are conjugate or not? Is there an algorithm to determine conjugacy for two-sided edge shifts? There is an algorithm for one-sided, but not for two-sided ones. We don't know if there's one or not. And even the ones, so, okay. Now, operator theorists have long, starting with the work of Kuntz and Krieger in the 70s and early 80s, started associating Cstar algebras to this setup to try to use Cstar algebras to understand the dynamics. So what they do is they build a Hilbert space whose basis is the space E infinity of one-sided infinite paths. So before I was talking about two-sided infinite paths, but now we're switching to one-sided infinite paths because it's kind of hard to act on two-sided infinite paths. So we're going to take a Hilbert space with that as an orthonormal basis. And then we're going to define a bunch of operators on this Hilbert space. So for each vertex V, we have an orthogonal projection to the span of paths starting at V. Okay? So maybe if you like vector spaces, so what does this operator do? PV, if I apply it to a path alpha, it's going to be alpha if alpha actually starts at V. So here's the start of alpha, and it's 0 else. Okay? So PV fixes infinite paths that start at V, and it's 0 on everybody else. That's what PV does. And for each edge, we have a type of operator called the partial isometry. And the way I like to think of it is you can think of an infinite path as like a stack. You can think of a stack which has a bunch of symbols on it, but the rule is that the symbols, the stack can have an infinite path on it. And the rule is that the infinite path has to really be a path in the graph. And then the operator E pushes an E on the top of the stack. So I put an E at the beginning of the path P, if that makes sense. So the path P had better start at the endpoint of E if this is to make sense. If it doesn't start there, then we say 0. 0 in this vector space world means garbage. So whenever we try to do a computation that's not legal, we say 0. Okay, but since this is a C-star algebra, there has to be an adjoint. When you use C-star algebras, you also have an adjoint. You're acting on a Hilbert space. And the adjoint has a simple description here. What it does is if your path starts with the edge E, you erase it. So this is basically pop E. So this is push E onto the top of the stack if it makes sense. This is pop E from the top of the stack if it makes sense. Okay, so if you're a computer scientist, you would think of doing this right away, but operator theorists also thought about doing this even though they probably weren't doing computer science. And these operators satisfy some obvious relations. And I'll tell you about those obvious relations on the next slide. And you use these relations to define graph C-star algebras. And then about 20 years later, people in ring theory use the same relations to define what are called Leavitt path algebras. Although Leavitt actually defined a special case of this for the full shift in the 60s before the operator algebra people. So it was first Leavitt, then the operator people, and then the Leavitt path algebra people. So I'm going to tell you what the relations are, and I'll try to convince you that these relations are obvious. I'll say, okay, so the graph C-star algebra associated to your graph is the universal C-star algebra with generators and relations. So don't worry, what is a C-star algebra? If you're happy about what generators and relations are, then you should believe, of course, one has to prove these things exist because they're operator algebras and not just rings. But basically, you know, things might become degenerate, but you can try to define universal C-star algebras by generators and relations. And our generators are these projection operators corresponding to vertices and these partial isometries corresponding to edges. And the relations are trying to imitate the relations that existed in the previous example. So first of all, these PVs are orthogonal projections. That means if I multiply 2 of them, that's going to be, well, it's going to be itself if they're equal and 0 else. And also the fact that the projections means that their own star, they're self-adjoint. This is because why is the product 0? A path cannot both start with V and W. Remember, PV fixes path starting at V, PW fixes path starting at W. You can only begin with, a path can only begin with one guy. So these guys are orthogonal to each other. There's no path in which they're both defined unless they're equal. So this is something that's true in our concrete example. Another relation says that if I have an edge E, then I put E at the beginning of some path alpha, I call it P. I put E at the beginning of a path P, then this thing starts at the source of E. So if I hit this by the thing which fixes stuff starting at E, that's not going to change anything. So that's what this relation says. It says that if I put an E at the front of a path, then it starts at the source of E, and therefore that projection doesn't do anything. Okay, this relation is the more interesting relation. It says that if I have some path P and I try to shove an E at the front, and then I try to erase F, I can only erase F if F is E, because otherwise it doesn't begin with F. And if I do erase F, I get back my P. And that's what this relation says. If I try to push an E and pop an F, it's 0 unless E is F, in which case it's going to be the identity on things which start from where E ends. Okay, so I mean, I don't expect you to observe this in real time, but these are obvious relations. And then there's one last relation, and this is the most important one. This is called the Kuntz-Krieger relation. And this is the first non-semigroup relation. All the other relations are semigroup relations. They tell you if you multiply two guys, you get either 0 or another guy. So these actually define an inverse semigroup. For people who know this, they define a graph inverse semigroup. But this last relation is really algebraic because there's a sum. And what does it say? If I have some vertex V, I look at all the edges that start from V. Let's say there's 3 of them, E1, E2, E3. Then what I'm saying is that doing this, oops, I did it in the wrong order. Maybe I should just make there 2, so I don't have as much to draw. Hold on. I'm not good at this writing on the screen thing. Let me just do 2 so I have only 2 to draw. What does this say? Well, if I have an infinite path that starts at the vertex V, it must either start with E1 or E2. This guy says erase E1 if it's at the beginning and then put it back, or give 0. This says erase E2 if it's at the beginning and then put it back, or do 0. If you have a path at V, it starts with either E1 or E2. So one of these guys will return the path you started with, and the other one will return 0. And so this is exactly just fixing the paths that start at V, which is what PV does. Okay, so this is just the fact that every infinite path starts with somebody. And the Leavitt path algebra, which is the ring theoretic analog, is you take some commutative ring R, and then you take the star R algebra with the same presentation. A star algebra just means you have an involution. So you should have that A star, B star is B star, A star. And other than that, it's an R algebra. Oh, okay, this is getting ahead of myself. These algebras are closely related to Thompson's group V, and more generally, the Higman-Thompson groups. This Kuntz-Krieger relation, this is actually the caret replacement, the caret rule. The rule in Thompson's group that says, that you can, if you have these carets, you can get rid of them. You can think of A star plus B star. This corresponds to an AB caret and then an inverse caret. It says that I'm going to erase either an A or B from the beginning of the word and then put it back. So I'm not doing anything. And it was proved independently by Berger and by Nekrashevich that Thompson's group, the Higman-Thompson's groups embed in the Leavitt path algebras for a loop. And if you take a general graph, you get something which is similar to a Higman-Thompson group, and they fit into Matui's world too. So there are a lot of actually simple groups that live inside of the group of units of these rings. And in fact, Leavitt algebras and their related algebras were eventually used to solve some isomorphism problems for Higman-Thompson groups and related groups. So I don't want to really talk about them, but these algebras are related to the Thompson groups, which shouldn't surprise you because we're talking about Cantor sets. So if you say Cantor set, you should see a Higman-Thompson group staring you in the face. Now, something that people in operator algebras and ring theory talk about, so I'm forced to talk about it, is something they call condition L. Condition L says that in your graph, you don't see this thing. You don't see a strongly connected component, which is a cycle. That's not allowed. So I don't know. So in a directed graph, this is bad. This is considered bad if you have a connected component with a cycle. I'm not going to explain why this is called bad, but it's bad. And it turns out that both the graph C-star algebra and the Leavitt path algebra are simple if and only if this weird condition L holds, that no strongly connected component is a cycle, and there's a unique minimal strongly connected component. So if you have a finite directed graph, there are certain strongly connected components, that you can flow into, but you can't get out of. And there should just be a unique one if you want this algebra to be simple. So for instance, if your graph is strongly connected and not a cycle, then the corresponding algebra is simple. So anyway, there's a nice clean criterion for simplicity of these Levitt path algebras and these graph C-star algebras, and they're the same. Okay, so I spent a lot of time talking about that, but that's okay. All right, so it's long been known that there are connections between the shift of finite type, graph C-star algebras, and Levitt path algebras for a graph. For instance, in symbolic dynamics, they look at something called the Bowen Franks group of a shift of finite type. And this is actually just the K0 group of the graph C-star algebra or the Levitt path algebra over any field. So this Bowen Franks group is what you do is you take the adjacency matrix of your graph, you take I minus A, this is an integer matrix, so it gives a homomorphism of abelian groups, a free abelian groups, and you take the co-kernel. So that's a finitely generated abelian group. And it turns out that's exactly K0 for these rings or C-star algebras, but it was introduced by Bowen and Franks as an invariant in symbolic dynamics. And it was shown, and it's known that under this funny condition L, the graph C-star algebra form and its continuous functions on its path space form a Cartan pair. So inside of the graph C-star algebra, you can look at the continuous functions on this compact space. That's a commutative C-star algebra, and it lives in the graph C-star algebra, and these guys form a Cartan pair. It will be a maximal abelian subalgebra. And it satisfies, and it lives there in the correct way. And Matsui and Matsumoto use this Cartan pair fact to characterize continuous orbit equivalence, which is an equivalence relation that people look at in symbolic dynamics for shifts of finite type using the isomorphism class of the Cartan pair. And they also characterize a different equivalence relation called flow equivalence of shifts of finite types, which is probably more important. In terms of the Cartan pair coming from, they actually replaced their graph with an infinite graph. You can also define these algebras for infinite graphs, but I didn't try. And so people began to ask, well, can you also use the Levitt path algebra to get these invariants instead of the C-star algebra? And so in 2009, I came up with I started to study an R algebra analog of these groupoid C-star algebras, which some people are nowadays naming after me, but I would prefer they should be called groupoid algebras. And it turns out there's a certain groupoid, GE, whose groupoid algebra over the ring R is this Levitt path algebra, and whose C-star algebra is the groupoid C-star algebra. And in the case that R is an integral domain, there was a series of work originally with Brown, Clark, and Anouf, where they were looking at Levitt path algebras. Then these guys went to more general groupoids. Then Carlson and Rout went to even more general groupoids. And then I got the most general result. And I also threw out integral domain and said, you can assume there's no nilpotent elements and no idempotents except 0 and 1. And these works basically say that you can recover the groupoid of a Levitt path algebra from the algebra and its distinguished commutative algebra, subalgebra, which turns out to be the continuous maps with the discrete topology on R. So you can give R the discrete topology, and then you can look at the locally constant or continuous maps into R and make an algebra out of it on the path space with pointwise multiplication. And you can again recover the groupoid and therefore the continuous orbit equivalent or the other results of Matsui and Matsumoto. And you don't even need this condition L. In the algebraic setting, you actually get more. And so that was, but one thing that was missing was a theory of Cartan pairs. If someone hands you an algebra and a commutative subalgebra, an R algebra and a commutative subalgebra, when is it one of these pairs coming from a groupoid? And so that's what we were going to address. But first, since this is a group theory seminar, I should talk about groups. So groups are a one object groupoid. Or people who say groupoids would say they are kind of a defective groupoid because they only have one object, but I would call it a monotheistic groupoid. It's a groupoid that believes in only one. So a group is a groupoid with one object. So I'm going to tell you what we're basically looking at, what it boils down for groups. So that G be a group in R an integral domain. So if you've been lost, you can come back now because everything is pure group theory for the next 5 slides. Okay, so the classical isomorphism for group rings, which was studied at least as far back as Graham Higman in his thesis in the 40s, is when does an isomorphism of group rings, RG is isomorphic to RH as R algebras, mean that the groups are actually isomorphic. And this is the simplest state-to-state version of the kind of thing we want to do, replacing groups by groupoids. So we want to know, can we recover our original object, the groupoid, from the algebras? We also kind of want to know which algebras come from groupoids, but let's start with this thing. So of course, if you have two finite abelian groups of the same order, their complex algebras are isomorphic by Fourier analysis. So you cannot recover a group from its group algebra in general. But also there's a problem that the complex numbers are way too big. So it's more hopeful that maybe the integral group rings being isomorphic might make the groups isomorphic. Because in a sense, once the integral group rings are isomorphic, then all group rings are isomorphic. The integral group ring kind of knows about all the other ones. And actually, it was a long time a thing in finite group theory to try to prove that if finite groups have isomorphic integral group rings, then the groups are actually isomorphic. And I guess sometime in around the 50s or so, even though there were a bunch of positive results, I guess Brouwer and others began to think it's probably not true. And Brouwer even suggested a program to disprove it. And in 2001, Hertwig found two non-isomorphic groups of order 2 to the 21 times 97 to the 28. I'm not making these numbers up, that have isomorphic integral group rings. So this was published in the Annals in 2001. I'm pretty sure he did not find this by a computer search because that's a lot of elements in your group. I'm pretty sure your computers would not want to play with that. So he knew what he was doing. He was trying to do Brouwer's program and he was able to do it. So you cannot hope to recover these groups from their group rings no matter what the base ring is. That's the moral of the story. Okay. So as far as I know, there seems to be only one method, one general method, that's not like these things specific to finite groups, that tell you that the group algebra determines the group. And this is the thing about trivial units that Giles Gardam spoke about last term. So if you have a unit of your ring R and you have a group element, then U times G is obviously a unit. Its inverse is U inverse G inverse. And these are called trivial units because they're so obvious you don't have to think about them. And we'll say that RG has no non-trivial units if every unit is just a unit of the ring times a unit times an element of the group. And you can also make this definition for twisted group rings. I'll remind you what's a twisted group ring on the next slide. And it turns out that for a twisted group ring, if it has only trivial units, so it satisfies the Kaplansky conjecture, then the group and the twist are determined by the twisted group ring as an R algebra up to isomorphism. So let me remind you what is a twisted group ring. So you have a group G and you have a normalized 2 cocycle. So I'm not going to write down the 2 cocycle condition, but it's just basically representative of the second cohomology with coefficients in R cross as a trivial module. And as an algebra, it has basis and bijection with the group, but I'm going to write delta G instead of G so that we don't think it's the group. But when you multiply 2 basis elements, you twist by the cocycle. So in a standard group algebra, delta G, delta H would be delta GH, but here we twist by the cocycle. In particular, if the cocycle is trivial, if it only takes on the value 1, you get the group ring, but it's more general. And then again, because this cocycle takes values in the units, if I take a unit times a group element, that's going to be another unit. So this is the group of trivial units. And we have the central extension. We have R cross lives inside of the trivial units, and the quotient is G. And this is exactly the central extension which corresponds to this cohomology class, right? A cohomology class corresponds to a central extension of G by R cross, and it's exactly this one. That's how you multiply the things, right? So this is the central extension. So if you can recover the central extension, then you can recover the cohomology class. And I'll say that the twisted group ring has no non-trivial units if the only units in the group ring are these obvious ones. And what I claim, and this will be kind of the semi-proof in the class, in the talk, because everything else I want to say is a groupoid version of this argument, which is way more complicated, but it will give you the idea. Suppose that I have a group ring with no non-trivial units, a twisted group ring. You can pretend it's a group ring if you don't care about the twist. And suppose I have some other twisted group ring which is isomorphic to it. Well, then you see the this guy here, because I have only trivial units, this is the whole unit group. And these guys are some units. So my phi, my isomorphism, has no choice but to send my trivial units here to my trivial units here, because that's the only units that I have. But also this map, so this map phi is injective because phi is an isomorphism, but it's actually surjective because the trivial units span the twisted group ring. So its image here has to span this group ring. And that means I have to get at least a pre-image of every element of G. So this thing is actually surjective. And so you see that I actually recovered my entire exact sequence. And therefore, since that exact sequence tells you the cohomology class, we can recover the group G and the cohomology class from the algebra isomorphism. So this is the only idea in this talk. And then we basically do the same thing for groupoids once I tell you about groupoid algebras. So then you might say, well, are there any groups for which you have no non-trivial units? And the answer is yes. They're the same ones you know for ordinary group rings. So if a group G has what's called the unique product property, this is the advantage of speaking to group theorists instead of analysts, as you guys all know what this is. This is this weird thing that if you take two finite subsets of the group and you multiply them, then somebody in the product can be uniquely expressed as somebody in A times somebody in B. So if you have this thing, then the same argument that you already know for ordinary group rings will show you that there are no non-trivial units in the twisted group ring too. And in particular, left orderable groups have this UPP property, and therefore they have no non-trivial units. So that includes torsion-free abelian groups, free groups, braid groups, and lots of other groups that you know are left orderable. Of course, left orderable groups are torsion-free or UPP groups. Let me just add that this is not a necessary condition. Higman showed that if ZG has no non-trivial units, then if I take its direct product with a two-element cyclic group, it also has no non-trivial units. And he also showed that certain finite groups have no non-trivial units. So you don't need to be torsion-free to have no non-trivial units. So Kaplansky's unit conjecture, as everybody here knows, says that if G is torsion-free in R's integral domain, RG should not have any non-trivial units. But just this year, Giles Gardner placed an archive, a counterexample to the unit conjecture. He spoke about this last term. His counterexample was a certain virtually abelian, torsion-free virtually abelian group. He showed that there were non-trivial units over the two-element field, but other people have since showed that his example has non-trivial units over every field of a positive characteristic. It's still open in characteristic 0, whether his group has any non-trivial units. But this means that the no non-trivial units phenomenon is less widespread than previously, maybe believed is too strong a word, maybe hoped is the better word. So that means our results might not be as widespread as we would like. But anyway, it's still a reasonable property. So now I'm going to tell you about groupoids so I can tell you a little bit of what we did. I don't think I'm going to be able to tell you our full-fledged abstract theory or Cartan pairs because it's too much ring theory and not enough group theory. But I will tell you what is a groupoid. A groupoid is like a group, except you can't multiply all the objects. So officially is a small category. That means it's like that the category is actually a set. It's not something like the category of all sets or all spaces. It's like a category that doesn't have size issues. And everything is an isomorphism. Okay, so basically what it means, you should think about the fundamental groupoid of a space, right? So you have x's, you have y's. If your arrows line up, you can multiply them. And you have the associative law, and you have inverses, and you have identities at each object, x. But one thing that's convenient when you do analysis in ring theory is we identify the object x with the identity 1x, right? There's no real reason to make the category multi-sorted and think of the objects as a different set than the arrows. This is just convenient for doing algebra. And in this case, an identity is an idempotent. So as a semigroup theorist, I already wrote 1x times 1x, so I don't need to square it. These are the idempotents of the groupoid. They're exactly the identities. And they play a similar role in this theory to idempotents. And then the multiplication is only partially defined. And you have an inversion map. And notice with my funny convention here, the domain of this guy is gamma inverse gamma. And this is gamma inverse. Once I identify, well, this is really 1 of the domain of gamma. And this is 1 at the range of gamma, but I'm going to identify the objects with the identities. And so you can kind of view the domain and range algebraically this way. And The identities form a subgroupoid in which everyone is their own domain and range. So in the subgroupoid, all the arrows look like little loops. So it's not a very exciting subgroupoid, and everybody's an idempotent, but still it's an important subgroupoid. And a group is just a single object groupoid. You have one identity, which we usually call one, and then you have a bunch of group elements, you have inverses, and you can always compose them. So a group, if you look at the definition of a groupoid, a group is it's a groupoid without an identity crisis, right? A groupoid with many identities has an identity crisis, a group does not. But it turns out if you want to build an interesting algebra from a groupoid, you need to add in some topology, but not too much. If you have a discrete groupoid, then its algebra will be a direct sum of matrix algebras over group algebras, and it's not going to be very exciting. So a topological groupoid is just a groupoid with a topology for which the multiplication and inversion are continuous, just like a topological group. And I'm going to assume all my groupoids are Hausdorff. And then I can view the identities as having the subspace topology. And since I said before that the domain of gamma is gamma inverse, it's gamma, is it gamma? I said it backwards. I can never get this order correct. No, that doesn't erase it. Hold on. I said it backwards. I always get this backwards. I hope I said it correctly. What'd I do? I think I got this right. It's either gamma inverse, or I guess I get it. It's just composing left. I got it wrong again. Category theorists compose backwards. They do the opposite of a pass, so I get confused every time. So I think gamma inverse is the identity at the domain of gamma. So again, if some multiplication and inversion are continuous, the domain and range maps are continuous for free. That's the point I'm trying to make here. Okay, and the notion of étal means that multiplication is a local homeomorphism. So people in certain areas of math use étal as a synonym for local homeomorphism. And it turns out this is equivalent to the domain or range being a local homeomorphism. Étal groupoids were actually introduced by Groth and Dieck in the exercises of SGA. So you can always make a random reference to SGA to study toposes, but they're also commonly used by people who in operator algebras and people who do certain parts of the theory of Lie groupoids. So it's symplectic geometry and stuff. In fact, you can even define orbifolds in terms of étal groupoids. And if you pick up Breitson and Helfliger's book, there's a whole part at the end of the book about étal groupoids, because Helfliger did a lot of étal groupoid stuff. And the kind of groupoids that are important for us are étal groupoids with the property that their unit space is like a Cantor set. It should be locally compact and totally disconnected. This is what happens like when you take the path space of a shift of finite type. And these are the ones for which you can do something interesting in ring theory. The reason why is if you take a ring R and you give it the discrete topology, and then you look at a continuous map from a space X into R, if it's going to be continuous, then because the topology is discrete, it's going to kind of be constant on connected components. So if you want to have lots of functions, continuous functions from X to R, you want your space to be totally disconnected. Otherwise, you're not going to have very many functions. And it turns out that this subset space of units is always Clopin. So here are some examples. So if you have a topological group G, then it has a single object, a single identity, and this domain's a local homeomorphism. And the only groups that I know of which are locally homeomorphic to a single point is a discrete group. So in the world of groups, even though we're allowing topology, you'll never see anything new. On the other extreme, you can take your favorite space X and you can make it a groupoid by just making every element an identity. So you take your space X, you make every element an identity, you give it the topology coming from X, and then it's trivially a topological groupoid. And that gives you another example of an ample groupoid. The other one that people like to give as an example is if you have a group G acting on a space. I want it to be ample, so I'm going to make it totally disconnected. Then you can produce what's called the action groupoid or the semi-direct product groupoid. And what it looks like is the objects are elements of X, and if you have a group element, you just draw the Schreier graph. You draw the Schreier graph using the whole group, using G as generators, the whole group. And if you draw this Schreier graph, it actually turns into a groupoid. by just multiplying arrows in the obvious way. That's why we have to use the whole group so that we can make sense of multiplying it. And similarly, you have an inverse arrow that goes like this. And we use the product topology. And this is an example of an étale groupoid. Why is this an étale groupoid? I don't think I say, but this is a, if you look at the projection, for the domain map just is the projection. And so this is actually a covering map. It's not just a local homeomorphism. This is a principal G bundle. So it's a covering map. So it's even better. Okay, so these are examples. And there's also one which is too complicated to explain that you associate to a graph. Okay, so the way you build an algebra from one of these groupoids, and this is what I've been thinking about for the last 10 years, is as an R module, you just take the continuous functions from G into R, giving R the discrete topology. So you take continuous functions with compact support. So that means the thing is not mapping to 0, it should be a compact set. And then you take the convolution product, which just means that the value on gamma is you factor gamma in all possible ways, and you apply F to the first half and G to the second. Okay, and this sum is always finite because of the étale of the local homeomorphism property of the multiplication and the compact support. The fibers of a local homeomorphism are discrete, and then when you hit that with the compact set, you're going to get finite. And if you look at the objects, G0 are clopin inside of this. And so the continuous functions with compact support on the unit space live inside. And since the only way you can factor an identity inside of the identities is itself times itself, basically the only way you can factor 1x inside of G0 is like this. And so this product turns into the pointwise product when you restrict to the unit space. And so that's the commutative subalgebra that's going to be appearing in our Cartan pair. And so examples of these include group algebras. In the case of a group algebra, your topology is discrete, so compact support means finite support. And if you write your group algebra as consisting of finitely supported functions, then this convolution is the way you multiply in the group algebra. Levitt path algebras that I mentioned earlier are also examples. The algebra of any inverse semigroup is also an example. Matrix rings over R are also examples. There are lots of examples. Nekrashevich algebras of self-similar groups. That's another example that I don't have time to talk about. Of course, I have to lie slightly. Some of the examples I just mentioned, you have to remove the Hausdorff assumption, but I don't want to do that, in particular for Nekrashevich algebras. If I take this group acting on a space case and I form the semi-direct product, then it's just the skew group ring. This group acts on the continuous functions from X to R, and then you get the skew group ring. Okay, so I think I'm not going to get so far in this talk because I did a lot of intro stuff, but that's fine. I'll try to give you at least some idea. I'll probably give you only half of the talk, but that's okay. So if you have a groupoid algebra, you can take a cocycle, a 2 cocycle. So a 2 cocycle is defined like in the group theory case, but the one rule you have to be careful about is you need beta gamma to make sense. So it's only defined on a pair of guys that you can multiply, and it should also be locally constant because of the topology. It should be continuous. And then you use the regular 2 cocycle rule, and we assume it's normalized. And the being normalized means that C of XX should be 1 for any identity. That's the generalization you would do of the group case. And then the groupoid, the twisted groupoid algebra is again the continuous functions with compact support. But now when we do the convolution algebra, we twist by the cocycle, just like we would in the group case. So this generalizes the twisted group ring construction. And because of the normalized property, oh, okay, see you, Zoran. Because of the normalized property, the pointwise, the continuous functions with compact support on G0 still lives in here. And actually, I'm slightly lying about the definition of a twisted groupoid algebra. It's actually more complicated than this. But for any reasonable groupoid, like a second countable one, it's equivalent. So if there are any actual operator theory people watching, they know I'm lying. But I don't want to get into it. So we had basically 2 goals. And I'm only going to talk about one of them because I'm running out of time. So goal number 1 is recovering the twist. So if we have our algebra A, our groupoid algebra with a twist, and we have this commutative subalgebra of functions on G0, can we recover the groupoid and the twist from our algebra? How much time do I have, Ilya?
Actually, you still have 15 minutes, so I think you have a
Oh,
lot.
we start. Oh, we go a full hour, not.
Yes, yeah.
Oh, that's good. So this is kind of, so what I'm talking about, first of all, is like the group ring isomorphism problem I said before at the beginning, right? When can we recover a group from its group algebra RG up to R algebra isomorphism? But now R is getting replaced by B, and our group ring, or our twisted group ring, is getting replaced by A. So that's the first thing we want to do. The second thing is I want to give you axioms, but I'm not going to have time, but we do it in the paper. We give you axioms on a pair of A and B that tell you when they come about in this way. So that if you had been given Levitt path algebras and you didn't know there was a groupoid, the axioms would tell you there's a groupoid. So those are the two things. And the key thing that we need to do is we need to generalize this Kaplansky conjecture and figure out what is the analog of trivial units for these weird things of groupoid rings. And basically, trivial units are going to get replaced by an inverse semigroup, because everywhere I live, inverse semigroups will appear. So a group has only one identity. And so the unit space of our group, if you have a group, if G is a group, the unit space of our group G is just the identity. And so if I look at functions from the identity to R, that's just the ring R. So the twisted group ring and the subring of things supported on just the identity is an example of a pair. And we saw that the no non-trivial units condition lets you recover the group and the twist from the pair. So the question is, what is the analog of units in the groupoid setting? It's not units, it's something more complicated. And the answer is we take the inverse semigroup of normalizers of B. So we're going to look at a certain inverse semigroup of things which normalize in an appropriate sense the subalgebra B. So B lives in A, and we want to look at things which normalize that. And it will turn out, under the situation we're looking at, to form an inverse semigroup. And certain elements will be obvious normalizers. And the condition we're going to want is that the only normalizers are the obvious ones. And for a group ring, the normalizers are exactly the units and 0. And the trivial units are the obvious ones. And then the other thing we want to know is which things come from a groupoid, but that I'm not going to have time for. So the setup basically in our situation is R is an integral domain, A is an R algebra. I didn't say it, but most of my algebras don't have identities. And B should be a commutative torsion-free subalgebra. So it should be torsion-free as an R algebra. And it should be generated by idempotence. And it should have a technical thing that it almost contains an identity for A. So this was too technical, so I'm not going to get into it. In the theory of Cartan pairs for C-star algebras, the big C-star algebra A does not have an identity, but the smaller C-star algebra B contains what's called an approximate identity for A. So the condition here is that B is a direct limit of unidal rings. It's not a unidal ring, but it's a direct limit of unidal subrings. And every finite subset of A has some element of B, some idempotent of B, which works as an identity for it. So it almost has an identity. And in particular, you have these conditions if you take a twisted groupoid ring. So if you have what I call a groupoid pair, a pair coming, an A and a B coming from a groupoid, then they satisfy these properties. And now I can tell you what is a normalizer. So a normalizer is an element of A, which has an inverse element, which I call N prime, which satisfies the inverse semigroup notion of inverse, or the von Neumann-Moore-Penrose notion of inverse, and which conjugates B on both sides. You have to do the two sides separately, back into B. So this is what people, like in inverse semigroup theory, you can talk about a normalizer, and this is what you need. This condition about the local units and that B is commutative guarantees you the idempotence commute and force this to be an inverse semigroup. You have to do something to prove that this is an inverse semigroup, but it is an inverse semigroup. For instance, if I take a group ring, so just think of a group ring, then the normalizers are exactly the units and 0. So remember, B is just R. If I have some sum of group elements, and then I hit it by 1, and then I have some other sum of group elements, and I'm supposed to actually get a scalar multiple of 1, then you can figure out very quickly that these things have to essentially be, units. Okay. And inverse to each other, or 0. All right, so these are so they generalize units. The twisted groupoid ring is spanned by normalizers. That's kind of needed later. And I need one last definition for the trivial unit, the trivial ones. So this definition is not going to make sense to you if you don't work with groupoid theory. But basically, the domain map is a local homeomorphism. The range map is a local homeomorphism. And that guarantees that there are going to be lots of open sets U, so that the restriction of both the domain and the range to U is injective. And the compact guys like this actually form a basis for the topology. And the characteristic, in a group, these bisections are singletons or empty. Because if I have two group elements, they both have the same domain and range. So if I try to restrict the domain and range to the set GH, it's not going to be one-to-one. And so the analog of a trivial unit is you can check if you have somebody which is supported on a bisection, and on that bisection it only takes on unit values, then it's a normalizer. And these are the trivial normalizers. So in a group ring, a bisection is something with singleton or empty support, and taking values in R times means it's a trivial unit. So this generalizes the trivial units to these guys. And so we say that this twisted groupoid, or the twist, satisfies the local bisection hypothesis. That's the name I made up. If the support of any normalizer is a bisection. So for a group, a twist on a group satisfies this condition if and only if each unit has is trivial. So if you satisfy Kaplansky's conjecture for a group ring, that's this local bisection hypothesis. So this is some funny groupoid version of it. So for example, if you have a group and you look at an object X, you can look at all the things which start and begin at X. And that's actually a group. And it's called the isotropy group. And the reason why is if I look at the special case of a group acting on a set, and I build my groupoid before, then the isotropy groups give you the loops. So it's called the isotropy group. And one thing I proved, originally I proved it for the non-twisted case, and then we generalized it to the twisted case, is if the set of points X for which this guy satisfies this isotropy group has the unique product property, or it's left orderable or something, if that's dense in the space of identities, then you get this local bisection hypothesis. So the Kaplansky conjecture for the group rings is inherited by the groupoid. And that's the main way we actually prove things have this property. So that's why it was bad for us when the Kaplansky conjecture was wrong. But okay, in the case of Levitt path algebras, you always get this because the isotropy groups are either trivial or infinite cyclic. Infinite cyclic group is left orderable, it's orderable, and the trivial group is orderable. So you get this Kaplansky conjecture, and so we get this property. So these things, these pairs of groupoids where you have this weird generalization of the no non-trivial unit thing, we call a concrete quasi-Cartan pair, and we have this reconstruction theorem. So at least I'll get up to one of our two theorems. And basically it says if you have a groupoid which is a concrete quasi-Cartan pair, so that means it has like no non-trivial normalizers. That's the right way to think about it. So it's the generalization of the Kaplansky property. Then whenever it's isomorphic to some other twisted groupoid ring, your original groupoid is isomorphic to the other groupoid, and once you identify them, the cocycles are cohomologous. So there's some theory of cohomology for groupoids, and you have the same kind of theorem. So what this says is basically exactly what Renault and Kumjian proved in the Cstar setting, and Feldman and Moore proved for von Neumann algebras. Namely, if you have a groupoid which gives you one of these Cartan type pairs, or we call it quasi-Cartan because we can do more generally, then you can recover the guy from the algebra. The other theorem, which I don't think I have time to explain, because I'm guessing I have only 5 minutes at best left, is the other direction, which tells you which algebras actually come from a pair of groupoids with a quasi-Cartan pair. So what we would call an abstract quasi-Cartan pair. So let me check. How many more minutes do I have? I want to see if it's worth trying or if I should just not try. I'm guessing I should just not try.
I don't know, at least 5, as you said.
At least 5. So maybe what I'm going to do is skip the technical definitions and just tell you that there is a definition. So I should say for this theorem that in the case of untwisted groupoids, this result was proved by me, and the twist is the new bit. But the thing is, for the theory of Cartan pairs, you always get a twist. You cannot guarantee that you actually get an untwisted groupoid. So I don't want to get into this. So people in operator theory. So if you go to Feldman and Moore's paper, the key thing in their definition of a Cartan pair is what's called a conditional expectation. Conditional expectation for commutative von Neumann algebras correspond to conditional expectation in measure theory. So that's where the name comes from. If I look at this definition, it actually reminds me of what's called the Frobenius algebra in ring theory. It's the condition that you have something that behaves like a Frobenius form in ring theory. But anyway, so maybe it's just not worth it. I think that you're not going to be able to absorb the definition. But so let me just give an example without a definition to try to explain the ideas. Let's take n by n matrices over R as our A, and B diagonal matrices, which is a commutative subalgebra. Okay. First of all, this is spanned by idempotents, right? The diagonal matrices are spanned by guys that are idempotents that look like this. So they fit into my nice framework of being spanned by idempotents. It turns out that the n by n matrices are spanned by the basic matrix units like this. And these guys form a well-known inverse semigroup called the Brent inverse semigroup, and they normalize the diagonal matrices. And the inverse is just the transpose. The inverse is the transpose matrix. And the general normalizers are what are called monomial matrices. They're matrices which have a single non-zero entry in every row and column, and that non-zero entry should be invertible in the ring. So those are the normalizers. And the diagonal matrices are a maximal commutative subalgebra. That's sort of where the original Cartan type theory comes from. And then it has this funny conditional expectation, which I don't have time to define. And this is an example of a Cartan pair. So the key points in a Cartan pair, which I don't have time to define, is the commutative thing should be generated by idempotents. The big algebra should be generated by normalizers of the small algebra. For a Cartan without the quasi, it should be a maximal. I don't want to explain the quasi thing. And you need this funny conditional expectation, which is a generalization of Frobenius's observation that group rings are Frobenius algebras. And this is supposed to come from a groupoid according to our theorem. And what is the groupoid? I'll do it for 3 by 3 matrices. You have 3 objects and you have essentially a single arrow between any objects. So this is what the groupoid looks like. And the algebra of this groupoid is n by n matrices over R. And so the general theorem, but I didn't give you the definition, but at least I'll state the theorem, is that if you have what's called an abstract quasi-Cartan pair, which I skipped the axioms, then it comes from a twist. There is a groupoid G and a twist and a linear isomorphism of pairs, an R linear map that sends A to this guy and B to that guy. And the groupoid and the twist and the groupoid are unique by that reconstruction theorem. So there is this axiom system, which I didn't have time to explain, that tell you when a pair of guys come from this. And so this is the ring theoretic analog of Feldman and Moore for von Neumann algebras and Renault and Krumjian for Cstar algebras. And so that's all I have time to say, and it's probably more than I needed to. So I'm sorry I repurposed an analysis talk for group theory.
That's all right. Okay, well, thank you very much. Let's thank Ben. Okay, now the floor is open for questions. So if there are any questions to Ben, please ask.
I mean, I realize it's not fair because I threw a lot of definitions people don't know, so it's completely okay for no one to ask a question.
So I actually had kind of a question. It's a little diagonal, but I mean, there is this property of not having of only having trivial units, right? You know, I forgot what you call it, Kaplansky property, whatever it was called, which was more or less for groups related to torsion freeness, right? You know. But you also mentioned earlier in the talk that in the beginning of this business, people were actually interested in this problem of finite groups when the group rings can be used to recover the groups.
And then you do have torsion.
So what did people do there? I mean, they must have used different arguments, right? You know.
Yes, they used very different arguments, of which I am not sufficiently familiar with them. But they're special to finite groups, and you know they started with finite abelian groups, and then they kind of moved up the hierarchy of different kinds of groups. So, but yeah, the techniques have nothing to do with I mean, the only technique in the torsion-free case is really this unique product property that you want, that when you multiply the supports, there's one guy that sticks by itself and therefore cannot disappear. Or actually you need two guys, but the unique product property actually implies that there are two guys that survive. But for the finite case, they're really playing with finite group theory. And so they could do, I don't remember whether it's true for all finite nilpotent groups. I think that one is a solvable group, that example. It has only 2' divisors. But I think for nilpotent groups, I'd have to double check. I think it was okay. But I don't remember off the top of my head. But it's definitely very different. And Higman already in his thesis had quite a bit on that.
Okay.
So he was looking at the finite case, and he was looking at quaternion groups and things like that. And that was, he came up with the non-trivial units there. And there are examples with no non-trivial units in the finite case too, but it's very rare. Like the quaternion group and exponent 2 and 3, maybe 6, something like that. So Hegman gave a complete list of finite groups which have no non-trivial group units in their group ring. So no non-trivial units is weaker than the torsion, you don't need torsion free for that.
Right.
It's not like 0 divisors where as soon as you have torsion, you get them.
I see. Okay. All right. Any other questions? Okay, let us thank Ben again then. Thank you.
Yeah, I mean, I didn't mention it, but maybe it's worth mentioning. When you recover the groupoid, you also recover, in the case of these Levitt things, the Thompson groups and those things. So the Thompson groups, the groupoids, the algebra pair, they basically carry the same information. That's how people were able to do the algebra stuff to solve some isomorphism problems for Higman-Thompson groups. The Pardo and company. And then I think eventually maybe they moved up to Bryn-Thompson groups too. So somehow the fact that you can recover from these algebras, the groupoids, and therefore these groups. So Maturi and Matsumoto Maturi rather spends a lot of time on showing that these groups he considers, which usually have a simple commutator subgroup, basically recover the groupoids as well. So that's a big part of his thing. He calls it like his reconstruction theorem, or so I forget what he calls it. So there's also a connection with these kind of simple groups related to topological full groups, which I didn't get into.
All right, very good. So I'll stop the recording now in case people